I had to start a new streaming. Okay. YouTube kicked me out. Well, probably they are limiting. I'm not sure that I'm new to this streaming thing. It's been over an hour or so. YouTube kicked me out. Boom, boom. Hi again. So people are back. We still have a few minutes. You're scaring me, brother. For animal abuse. Well, either that or we get bitten, you see. Let's wait for the others to join. Bolts coming from Rakan. Ooh, tech savvy. Yeah. Welcome back, people. Break ended 2 minutes ago. Yeah, we are back. Ew, that's a snake. Where are the others? Yeah, YouTube ended our stream earlier. So it's easier to start a new window than wait for it to come back. So, why did I choose this name for my channel? Because this is my pen name when I was writing for the school paper back in high school and university. That's your answer, folks. Four more people. Where are they? Oh my God. Yeah, it's a Spanish name, just like my real name, Monterey. Do I like classes this way? Not really. I would rather have you face to face. It's a lot easier. You can always, you know, get the feedback that we want. But these are challenging times. We have to deal with it. You can see if I wasn't Omar sleeping. Is Omar even here? Did he lag in back? Hmm. Okay, Raid is here. Yes. Okay, so we might as well start. This will just be a quick discussion, then I'll leave it to your activity. Okay, maybe more than 15 minutes. In the end, you can finish. Hi, Nawab, you're back. So let's just let others catch up. So this is what we need to discuss now. Okay, just type in your questions later, and then we will deal with that if we have time. But we will go back to this. We will now be connecting the cell potential and Gibbs energy to equilibrium. Okay, the first thing that we need to remember, we said that chemical reactions, exergonic ones with the negative delta G, can actually do work, right? And this one here, the type of work that we are specifically talking about is the electrical work that we can derive from spontaneous reactions in a galvanic cell. So we should have a connection between the Gibbs energy and the cell potential. So, and that equation is given by the one from Faraday. Okay, so the cell potential is equal to the negative of n times the Faraday's constant, rather. We just started with D. That will be the G naught. Okay, look at that expression here. So that's your cell potential. Remember that for a spontaneous reaction, delta G is negative because it's the system doing work, right? And remember that delta G naught is your maximum work that can be derived from your system. So if we are maximizing the type of electrical work that we can derive from a battery, this is what we get. So N here is the number of moles of electrons involved in the electron transfer, the ones that go through the external wiring practically. So now we were introduced to this fancy F. I used to write it this way, not just the regular F, because this is your Faraday's constant. Michael Faraday is one of the scientists who actually introduced us into the concept of these electrochemical cells. So this is written in your formula sheet. That's 96485 coulombs of charge per mole of electron. So what does this practically tell us? If we pass 1 mole of electron through the external circuit, it is carrying with it a total of 96 coulomb. In trimester 1, remember what's the charge carried by the electron? It's negative 1.6 times 10 to the negative 19 coulombs. So if we add all of those, 1 mole is what? 6.022 times 10 to the 23 electrons. Put all those charges together, this is what we get. Around 96,485 coulombs. And of course, you already know this one here, which is your cell potential. If there's a knot here, that's your standard conditions. In other words, there are also non-standard conditions. So if there's delta G under non-standard condition, that is also equal to NFE, non-standard. So when does it become non-standard? When any aqueous solution is not at 1 molar, and if any gas is not at 1 atmosphere, these are non-standard conditions. Okay, so now how do we relate equilibrium? If you remember from chapter 17, we said that non-standard Gibbs energy is related to delta G naught plus RT ln of the reaction quotient, correct? So if we substitute all of these here, delta G will become negative N FE. Are you following this? And that means this will have negative N FE naught. Remember, delta G is different from delta G naught. E is different from E naught. These are under standard conditions, non-standard, okay? Plus RT ln of Q. So we will simplify this in terms of just the E. So if we divide everything by this factor here, we end up with what is known as the Nerst equation, which is named after Hermann Walter Nernst, okay? The same Nernst in the Nernst theorem in the third law entropy, if you remember his name. So that will be E is equal to E naught. Similar here. So we would know how much of the battery we will be able to use until this becomes 0, okay? When this becomes 0, that means your battery is dead. It has already reached equilibrium. So that's the significant thing that we can derive from this one. When your battery went dead, practically it's in equilibrium because no more net charge transfer, okay? So later on, we will be dealing with individual reactions. You already know what the reaction quotient is and what would be the implication while the reaction is ongoing, right? So naturally, you will be, this becomes 0 only if this entire quantity here, the second term in the Nernst equation, balances the value of the E naught, which you can easily get, right? That's the first thing that we did. We learned how to determine the E naught from the reduction potential table. And if you're given non-standard conditions, we'll be able to do the actual calculations and connect that with equilibrium. So here, we say that if your E is greater than 0, that is a positive value, meaning your reaction is proceeding spontaneously from left to right, okay, the way the reaction is written. If your cell potential, non-standard, is negative, so it's a non-spontaneous process, and therefore it's the reverse process that is occurring spontaneously. We've already learned that. And of course, if you have here your E0, you have reached equilibrium. Okay, so remember our secondary batteries are practically reversible. Okay, now let's do a little bit, a little trivia. Period 3 activities, the drawing especially. You can work on that. Can you solve period 3 activities, the drawing? If you want to go back to that. Okay, let me just go through activity 1 quickly so that you can go back to activity 2. Remember, you have to finish activity 2. You just have to draw Let me look at the questions if you want to. Okay. Yeah. For those of you who want to work with activity, you can do that now. Or we can look into the questions here. It says, consider the following table of standard reduction potentials. Let me just copy this. So for those of you who are still asking about how we answer the, remember this one, this is your previous activity, right? Which substance has the highest tendency to be oxidized or the reducing agent? So these are what happened. These are the ones given in the table. It has a potential of what? 1.47. B2 plus 2 electrons. B 0.6. C2 plus 2 electrons forming C negative 0.21. And D plus being reduced to D negative 1.38 volts. Okay? Now look at this one here. The question is, which substance has the highest tendency to be oxidized? Of course, the flip side is what? The ones that don't get reduced. So your focus, are you listening? When you are doing a reduction potential table, will be practically those that are here and those that are here, right? Because if you're reading from left to right, these are the ones that gets reduced. A3 plus to A plus, B2 plus to B, C2 plus to C, and so on. Now, among these four, A3 plus has the highest reduction, right? It will trump any others. If this is partnered with this has to be flipped because this is a stronger one in terms of pulling the electron. But the question was, which substance has the highest tendency to be oxidized, which is the reverse. So this is it, right? If you flip the reaction, D becomes D plus electron. Its oxidation potential is a positive 1.38 volts. Look at that. Its reduction potential is negative 1.38. So if you flip all of these will flip. The potential of C to be C2 plus is positive 0.21. The potential of B to be B2 plus, the ones on the right bottom. Which one gets easily reduced? The one on the top left. That's your answer there. Okay. So Ryan is saying, so the Gibbs energy concept also applies on electrochemistry. Of course, this is part of thermodynamics, Ryan. Chapter 17. Okay. So for those of you who already just work on the activity, just draw and submit. Okay. Well, those of you have questions, I'll be right here. So, Raed, how about number 2? Consider the following table of standard reduction potential, the same potential table. Which substances can be oxidized by B2 plus? That's a good question. Okay. Which substances can be oxidized? Let me write that question. Which substances can B2 plus oxidize? So if that is the question that we're asking ourselves, so that means B2 plus gets reduced to B. Remember, if you have read the material, anything below gets oxidized by flipping them. In other words, B2 plus can oxidize C to C2 plus. B2 plus can oxidize D to D plus. But B2 plus cannot oxidize A plus. Why? Because A3 plus is a stronger one in terms of electron pool. So A3 plus would prefer to be reduced rather than being oxidized in the reverse process. That's the reason why they are listed this way. Okay? Remember, the table says reduction potential. What is their tendency to be reduced? The one with the highest value gets reduced first. Okay? So if all of these are available for reaction, A3 plus gets reduced first because it has the highest reduction potential. Okay? So again, when you're revising for this, you say anything that is below that reaction is a potential oxidation half. I just have to flip that. But remember, when you say flip, you're starting from the reduced form to the oxidized form, right? So this reduces this reduces that, or you can say this, okay, oxidizes rather, this oxidizes this oxidizes that. So that's what you have here. Okay, what else? Ryan has a question. If we flip, wouldn't the value be positive? Yes, we flip. Every time we flip the positive, but we have the positive value. Let's see. If B2 plus gets reduced in the process, it is actually oxidizing something. Remember, redox is reduced as it is. If it oxidizes C, so your reaction becomes what? C2 plus. Can you see it from there? Plus 2 electrons. It becomes positive 0.21 C. You end up with a 0.81 volts. That's a spontaneous process. Yes, you have to compare before flipping. What's this? If we flip D, wouldn't the value be positive? Yes, we have that. Or do we compare them in there? Abdul Malik said you must compare before flipping. That's the reason why. You should know which one is stronger. Okay? So what's our generalization? If you're looking at the reduction potential table, if you look at a particular reaction, anything below those is a potential partner in the flip side. You need to flip that, making them oxidation. So this will oxidize this will oxidize that. A3 plus, which is the strongest one here, the strongest oxidizing agent, it oxidizes B, oxidizes C, oxidizes D. D is the strongest reducing agent. It will reduce anything on top of that, right? D reduces C2 plus. B reduces B2 plus. D reduces A3 plus. Because you can totally have your own list of oxidation potential. If I flip all the reaction, what I have is an oxidation potential. Okay? So it's 11:30. I would rather for you to work on your activity. I will just wait for you for your questions if you have some. You have the last 30 minutes to work on that activity. It's easy. You just have to construct your cell, take a picture, and submit. Let me just check what's happening here. Okay, so 2 people have already submitted their work. That's fine. So just chill. We will have actual calculations on Nerst equation in our next meeting. I will upload a digital copy of chapter 12 soon. And then I will populate also all the slides from chapter 14. I mean, my PowerPoint, I will put that in Schoology, so don't worry. Do we have to draw the ions in the solutions in the voltaic cell? Yeah, Abdal Al-Mahini, you can concentrate on the ions that are part of the reaction. You can remove the counter ion, okay? Do I include H2O2 and H2 as the cathode? No, the cathode should be a solid, a conductive solid. So in the case of that cell where H2O2 and H2 are not solid, we call in our friendly platinum to do the job. Okay, so you have to put platinum as the electrode. Is it not to just draw one of each ion present in the solution? Yeah, that's fine, but you should show the electron movement, like the anode, just like what we did, electron pushing, then you produce cations, so and so. You have to balance the reaction for the overall reaction, yes. So what we need to have is the oxidation half reaction, reduction half reaction, overall cell reaction, the E naught of the cell, your diagram. So platinum is the electrode, but both H plus and H2 are aqueous species and they're all included in the cell notation. Yes. To answer your question better. What's the reaction? H2O2. Okay. So H2O2, don't forget about the H plus, bother. There are three liquid species there. We need to include water in the notation. Why? Because it's part of the reaction. It's not just the regular solvent that we're talking about here. H2O2, H plus, and H2O. So there's no solid in there. That's why we call in platinum to do the job. On the other hand, the other reaction has a solid in it, which is conductive. So we don't need an additional electrode for that. It can work on its own. Let's erase this part here. Let's see what's happening there. H2O2 dissociates into O2, right? So we include the oxygen in the cell or we omit it. No, we don't. We don't produce oxygen in this case, right? And the reaction given to you, what does it have? No, it says the reaction that we need is H2O2 reacting with H plus producing water. Did you get that, Ryan? That's a different reaction you're talking about. Okay? The half reaction that we're talking about here is the reaction between H2O2 and H plus. No oxygen. That's a different reaction. Yep. We only include what is shown in the reaction. Okay. So what is that reaction that we're talking about? This is the H2O2 plus 2H plus 2 electrons, 2H2O. So that's one of the reactions that we need to consider. What's the other one? It's silver. Ag plus electron, Ag solid. So it's given 1.78 here. And positive 0.8 here in terms of reduction. So obviously this is your cathode half because this one has the high reduction potential. So this has to flip, okay? Okay, I can unplug this. Of course you can, unless you're already in the bathroom, Yasid. Even online, you have to go to the bathroom. Do we include water in the drawing? Yes, because it's part of the reaction. In cases where water is part of the reaction, yes, Ryan, we need to include that as a species. Even in the cell notation, we have to see that. So in one compartment, yeah, I think if there's something wrong with what you've written, then I'll give you feedback on that. When it's perfectly fine, then you know what it means, right? So I'll reserve my feedback for those that need a little bit of correction, right? We're talking about feedback. Thank you, Omar. Let's see. Whose work is that? See? It's reflecting. You want your feedback now, Omar? The cathode should be on the rightmost and the anode should always be on the leftmost, right? Always like this, right? Anode, anode half cell, salt bridge, cathode half cell, and then you have your cathode. So this is our internal circuit. So this anode is connected to the cathode in an external wire, right? And the electrons are moving from the anode to the cathode. So this is how you should be writing your cell notation. What's for lunch, everybody? My fettuccine pasta is waiting for me. Yum, yum. I didn't have time to eat my snack. Racing Canes. What's that? Kabsa, kabsa. I haven't eaten kabsa for a while. The best one I tasted was the one brought by Mr. Shataiwa in the faculty room before, but it was a long time ago. They will open Subway next to Starbucks in Kings by the end of the year. Oh, that's a welcome treat, Subway. Batteries to complete the setup. Your cell will not work without the salt bridge. What salt should you use? It's the usual stuff. You can say sodium nitrate. That could work. Na plus, NO3 minus. That's the usual go-to salt bridge saturated sodium nitrate solution because sodium ions will definitely not be part of a redox process. It's very difficult to generate sodium metal from sodium ions. Oh, he cooks. That's good. Fried chicken restaurant. We want, yeah, I like fried chicken as well. But we have Popeyes now inside, though it's just what? A small one. What do you call that? What's laham mandi? You mean lamb, Muhammad? Okay, you can change if you want. You still have time, but this one's fine except for the notation, I guess. Where is Racing Canes? I'm intrigued. What type of chicken do they serve? I love matabaldo, like dipping bread into it. It's next to Tamimi. Tamimi here, close to us. Is that the Tamimi you're referring to? Okay, let me check. We have a complete set. Okay, we're still waiting for the others. We'll see. Do we separate the water liquid from an liquid? No. So we only use commas, right? So how do it look like, Abdul Malik? It's like something like this. You have your H2O2, aqueous, separated with a comma. We cannot use a bar because they are all in the same mixture. H plus like that. And then we have your liquid water. And then your electrode there and your salt bridge somewhere, something like that. Yeah, so to answer those questions, you just put a comma because they are all in the same mixture. Look at that. H2O2, H plus, H2O, all of them are in your aqueous mixture. So we only use comma because they are coexisting. We only use the physical boundary, right, to differentiate a liquid from a solid and a solid and a gas. What if it's between two solids, by the way? Can we use a comma? Oh, I'm throwing the question to you now. What if we have two solids in one of the half reactions? Because that can totally happen. We have the silver chloride reaction. What do you think? Can we write, say, AgCl comma Ag as a solid? Or will it be more appropriate to write AgCl bar and Ag as a solid? Which one is correct? Yes. Even if they are both solids, their structures are different, right? So this is the correct way of separating two different solids. So we still use a physical bar, okay? So only those in the liquid gets to be mixed completely. So a gas will always have a bar with something else. A liquid will always have a bar with a solid and a gas. But the liquid mixtures that we're talking about in class is always what? Aqueous. So once it's in the liquid state, all of them are in there. So we separate them by commas. Yeah, the physical bar is not for just for physical states, Ryan. It's physical boundary, right? So two solids are not the same. Unlike if they are dissolved in the liquid, they're all in one phase, the liquid phase. But sugar put together with a salt, they are two different solids. They are not in the same phase, right? You can see the different type of granules. Is everybody done? We're almost done, right? Let me refresh my Schoology. 1, 2, 3, 4, 5, 6, 7. So half of you. Okay. Keep on doing it. Still have 20 minutes. No worries. Drawing it in paint, you wish. Just sketch it. Okay, but then let me see. Wow. There's color in it. So silver is our anode, correct? Platinum is our cathode. So battery shown H plus water H2O2 there, sodium nitrate, blah blah blah, electron moving there. Yeah, it looks good. Good job. Where is Fawaz? What did you say, Muhammad? Of course, I don't understand anything Arabic, especially in the written form. How about Suleiman? Is Suleiman sleeping? Let's look at Muhammad's work. Wish number 2. Silver. Okay. Water platinum. Yeah. It looks complete. Good job, Muhammad. So everything is here. Okay, it checks Nawab's work. Wow, that's 8.58 megabytes. Loading, loading. There you go. Positive 0.98 volts, water, silver. Suleiman is being funny. Comma. Okay, so you put a bar between the aqueous and water, but that's fine. But it should be this way here. They're all in the same solution. Okay. And guys, remember these are all in liquid form. They cannot receive electrons without a wire or a metal or any conductive solid. So you need platinum there. At least you see it's working. You see there your reduction potential table. That's your notebook. But they even did it in computer. Thank you guys for doing your job well. What's happening here? Only a few more. 1, 2, 3, 5, 6. Let's check Abdulmalik's work. Yeah, I can see the platinum there. Good. Okay. Let me just put a comment. If you're done, yeah, you're excused. You can eat now for those of you who have submitted their work. Yeah, enjoy your weekend too, guys. For those of you who are done, you can rest. Regarding the lab experiment we did this week, are we supposed to do report for it or is it canceled? The term Mr. Garcia used for your report is suspended, which means that nowhere in the future is it expected to be submitted. But to be fair, it said it just suspends. So that means if we don't have to submit it today or in the near future, right? But our advantage compared to the rest is we experience the actual thermodynamic experiment. I'm not sure if others have even did the dry lab. So it's a good thing we were done before we do the virtual lab. So the answer to that is it's suspended indefinitely. Okay? So don't worry about writing the report for thermochem yet. Yes, you didn't. For was. How many more people are we waiting for? Almost everybody is done. Um, to answer your question, Mohammed, we have to wait for the directive of the administration if we will still be continuing with the virtual lab or the virtual classes, so to speak, next week. We just have to wait. Okay. At the rate the virus is spreading, we might be doing this for another week. I don't know. That's not definitive. So we have to wait for their announcement. Yes, everybody who's done can log out. Enjoy your lunch. So enjoy your weekend. See you when I see you, either here or here physically. We will see. Let's wait for their announcements. You too, Muhammad, Raid, Nawaf, Ryan, Said, not so Kevin. Is everybody done? Let me just check. I'll see you. Everybody's done. Ryan Algamdi. I don't see anything here. Can you say something to him? I think he already logged out. Omar says, remember it was the first to submit and the first to like. Okay. I may call you Kevin Algamdi. Suleiman. I refreshed my Schoology. Okay. Mr. Kevin Algamdi, can you tell Ryan Algamdi that I don't see any submission here? So only two people are left, Suleiman and Ryan. How come it says none here? No submission from Suleiman and Ryan Algamdi. Okay, no worries. Suleiman. Suleiman. Okay, Ryan's submission is here. Good job. We just erase the board and we're almost done here. Okay, so Suleiman has submitted. We're all done here. Enjoy your weekend, guys. So let's just wait for the announcement from the management if we were doing virtual classes next week or not. Okay, have a nice weekend. So I'm ending the stream now. Go and enjoy your lunch. Goodbye, everybody. You log out now. End stream. And